Good evening, class. All right, this time we finish up CPU scheduling. We'll look at the CPU schedulers used in Linux, Windows, and Solaris, and briefly talk about the evaluation of CPU scheduling algorithms. And one last time, here are the chapter objectives. All right, so here we go with Linux, Windows, and Solaris. So prior to kernel version 2.5, Linux used an order N scheduler, and in more modern systems, particularly servers, as N becomes large, that scheduler became unwieldy. So with kernel version 2.4, the scheduler was shifted to a constant time order 1 scheduler. As you can see here, it's preemptive, priority-based. It uses the basic structure of a multi-level feedback queue with one queue per priority. The priorities are such that a low priority number means a higher priority. So priority 0 is the highest priority. Priority 140 is the lowest priority. As you can see here, a higher priority number gets a larger quantum, execution quantum. So, let's think in terms of each task has its own quantum. The way this was implemented, there were two copies, in essence, of the feedback queues. One copy held those processes that hadn't yet used up their quantum in the current scheduling round. That was the active array, and then the expired array was where task entries were moved after they had used their quantum in a particular scheduling round. And then once all the tasks were on the expired queue, then the expired queue became the active queue, and vice versa. As mentioned here, response times were poor for interactive processes. There were quite a complicated set of heuristics used for determining which processes were interactive, and they didn't always work well. And once an interactive process once any process ended up in the expired queue, it could sit there for quite some time in a relative sense before it would get CPU cycles again, leading to fairly large response or latency times for some interactive processes. So the completely fair scheduler became the default scheduler in kernel version 2.6.23, and you might recall that for your kernel programming projects, you're using 2.6.27. So you're working with the completely fair scheduler. So there are a number of scheduling classes, and these are prioritized. So tasks in a higher priority class have priority over tasks in a lower priority class. And the basic idea of the completely fair scheduler is that if you have n tasks running, each task should get 1 over n of the CPU cycles. So the way the designer of the algorithm thought about it is that each process, each task has its own virtual CPU that runs at 1/n the speed of the actual CPU. Again, a smaller priority number means a higher priority. And there's this notion of a target latency, so a period of time over which all tasks should get some CPU cycles. You can think about it as the number of tasks increase. That implies that the number of context switches increase. So if the number of tasks becomes large, that target latency can increase. This notion of virtual runtime is how the processes are prioritized, with the notion that every task of the n tasks should get 1 over n of the CPU cycles. The scheduler tracks how much time, how much virtual runtime each process has gotten, and the process with the lowest virtual runtime will have the highest priority. And this decay factor is used to determine how much time on the processor a task gets for its quantum. So the decay factor is larger for a low priority task, meaning that its runtime runs out more quickly, and the decay factor is smaller for a high priority process, which means it'll have more CPU cycles on the CPU before the context switch occurs. And interestingly, for you fans of algorithms, the tasks are kept ordered in a red-black tree, which is one of the variations of a balanced binary search tree. And the key is this virtual runtime, how much runtime a process has gotten. So the highest priority process, the one with the lowest virtual runtime, will be the leftmost node in the tree, which you can see here. And when a task loses the processor, it's placed back in the tree, and what other task is in this position will be run next. And I'm sure you all remember from algorithms that with a balanced binary search tree, the search time is order log n, and in addition, as you can read down here, there's a pointer to this node that will help it be found a large proportion of the time. All right, this slide demonstrates real-time task priorities versus normal priorities. So you can see that real-time tasks are giving a higher priority than normal tasks. And as a question for you to consider, is Linux, does it fulfill the requirements of a soft real-time system or a hard real-time system? So Windows uses a multi-level queue with 32 levels, similar to what we've seen in concept in earlier sections of this chapter. And there's feedback. So if a Windows process expires its quantum, its priority is lowered, but never below a base amount for that scheduling class. And if a process has to wait, it doesn't use up its entire quantum. You can see that its priority is boosted, and for good interactive response, the foreground window is given a 3 times priority boost. Right, and here's a table of the Windows priorities. So in Windows, a higher priority number implies a higher priority. So here's Solaris, priority-based, 6 scheduling classes available. It would make sense that a given thread can only be in one class. Each class can have its own scheduling algorithm. The default time-sharing scheduling class is a multi-level feedback queue. So the dispatch table shows the priority 0 is the lowest priority here. Priority 59 is the highest, so presumably these are IO-bound processes, so they have a smaller time quantum. The CPU-bound process will have a larger time quantum, but of course it's the lowest priority. And then you can see what happens if a process running at priority 55 uses up its entire quantum, its priority is lowered to 45. But if it returns from a wait, its its priority is increased. So this figure simply shows the priorities of the various scheduling classes. And here are a few details which I'll skip. All right, so you probably remember you actually did perform using Gantt charts a little bit of CPU scheduling algorithm evaluation. For a real operating system with a real workload, there are several tools that can be used to evaluate various algorithms. So what you used was deterministic modeling. You were given a particular workload and ran the algorithm. Of course, going back for a second, if you're going to choose a particular algorithm and evaluate algorithms, you need to determine the criteria for selection, whether you're interested in throughput, completing as many processes per unit of time as possible, or reducing latency for a time-sharing system or what have you. All right, so here are, as you already know, some Gantt charts. Queuing theory and queuing models can also be used to help evaluate scheduling algorithms. I'll skip this slide. If you have a record known as a trace tape of the behavior of actual processes, then you can perform simulations of various scheduling algorithms. So here's how that would work. You would instrument an actual operating system to determine for your set of processes. For each process, CPU burst, IO burst, CPU burst, and record all that information. And then you can feed that trace tape into simulations for your various CPU scheduling algorithms. Or you could just go ahead and implement the new scheduler and see how it works. As this points out, most CPUs, schedulers, most systems do allow you to make adjustments to the CPU scheduling algorithm. So it gives you a mechanism rather than enforcing a particular policy. And that concludes Chapter 6.